So for this question, pointers, including the return address, are 4 by 12. Yeah, let's do 30 seconds left. Five, 4, 3, 2, 1. Okay, so there are lots of answers here. It's almost like a random choice. Okay, so first of all, the stack pointer starts off at 2000. And we're looking at a point in time, and I show you on the next slide, it shows this picture where we have the activation frame for 1, 2, and 3. And we're wondering what R5 is here. We know that this is, or maybe it's, we know it starts off at 2000. And it's up here somewhere. So it's going to be a smaller number. Remember, the stack grows by subtracting. So that rules out half the answers. So anything bigger than 2,000, that's certainly not right. And then the question is, well, how big are each of these things? Let's just take a look at slides now. And this picture here now is shown right here. So we know that when you're running in foo, stack pointers at 2,000. When foo calls 1, we know that the code that executes for that call and the code that executes at the beginning of the procedure together allocate an activation frame for 1. And the activation frame has to be big enough to store all of 1's local variables, arguments, and the saved return address. And so you can see a picture of that. There's just one local variable. It's the local variable I and the return address. And I said return address is 4 bytes. So the total size of the activation frame for 1 is 8 bytes long. So that means that, you know, in fact, both of those are going to happen. You remember last time there was a picture here where we had the call and the callee. Both of those are going to happen here. This is going to be subtract 8 from the stack pointer in the very, very beginning of 1. And that gets us when 1 is executing that we're at 192. Now you just repeat this. 2 has 2 local variables, so the size of that is 12. So you subtract 12 from 192 and you get 180. And then the final one has 3, but it also has, it's different from the other ones in another way, which is that it itself doesn't call another procedure. So in fact, in this case, it's possible that the compiler will not generate code to save the return address. This is called a leaf procedure. A procedure that never calls another procedure might keep its return address just in a register. If it's small enough to do that, the compiler might do that. So it's possible that you get the activation frame on the left and the correct answer would be 168, because this is illustrating that particular optimization that the compiler might do. Or it might just be, you know, even though it doesn't maybe need to save return address, it does, and you get 164. Questions about this? So either of those two answers is fine.
For 1, why aren't we saving the address for 2? Jump to 2.
Well, let's look at that. That's a really great question. So here we have the call. So we're in foo. And we have the call to 1. And here's 1. And 1 will do a bunch of things, and then it's going to return our 6. And we know the call to 1, what does it do? It saves the return address in our 6. Okay. And it jumps to 1. Now, it has done nothing yet with the stack, right? Now, it also would, if there were arguments, there is the argument build that happens here. But there are no arguments, so nothing happens here. So in fact, the activation, the stack pointer is still pointing at foo's activation frame when you get here. And then when we get here, we have to, at the beginning, make room for the local variables and the saved return address, so we're going to have -8. And then store the return address, R6, onto the stack. Okay, so that's these two lines create the activation frame. I've got 2 positions in it, one to store the value of I, and the other one to store the return address. And here I'm saving R6 there. So the activation frame has a pointer to code, but it's a pointer to right here. And you ask about, what about the address of 2? Well, that actually was just in the jump, or 1. Be the same. Did I answer your question? Very good question. Other questions? So we talked a little bit earlier about the role that registers can play in a procedure call when we describe how values are returned. So if one actually returned an int, then somewhere towards the end we'll put something into R0, and then somewhere here we'll take something out of R0. R0 being the register that's used to convey the return value from the callee back to the caller. And that's typical. It's not always that way, but it's typically that way. There's other optimizations. We just saw one on the previous slide, which is that if you have a leaf procedure, procedure doesn't call another procedure, you might not save the return address. And there's one final one, which I'm going to illustrate on the next slide, which is sometimes you can completely avoid the stack and just use registers for everything. So this particular procedure has a call so the top part is the procedure foo. It calls add two numbers. And you can see the control flow here with the green arrows, showing you here's the procedure call, that code, sets up, puts the arguments on the stack, that makes the call. This is the add, which reads these two things from the stack, adds them together, jumps back here, and then we put the answer in R0, and then we save that into memory. And the observation I want you to make here is that here I'm saving register value or argument values into memory, and right after that I'm loading them back. So this is a lot less efficient than if I just added the two numbers in foo. Because I'm putting the two numbers I want to add into memory, and then an add taking them out. And so sometimes the compiler will look at that and say, well, I can make, there's the return value like that. I can make this faster in a couple of ways. So one way is you see there's no prologue or epilogue in add. Why is that? Well, add doesn't call anything, so it doesn't need to save the return address, and add doesn't have any local variables. Or even if it did have local variables, the compiler might, for a small procedure, decide to just use registers for them. So it doesn't actually create an activation frame for add. Add just runs on foo's activation frame. But that doesn't solve the problem of wasting the memory access here and then saving here, store, load, load. But the code on the right does that. So the code on the right is an alternate way to implement add. Now the compiler can only do this if it sees add and foo in the same file. Because it has to coordinate how it's calling a procedure with how the procedure is implemented. In this case, it's decided to switch from using memory to just using registers for the arguments. So rather than creating the activation frame, the part of the activation frame that has the arguments, and saving them there and then loading them here, it just passes them in registers. So it uses register 0 for the first argument and register 1 for the second argument. And now you can see add is just add and then a return. So that will execute much more quickly. Here again is the control flow, so you can see it. Now there is actually one further optimization the compiler might do. Can you see what it might be?
Just put add in the normal thing.
Yeah, I mean look at add. It's a procedure that has two statements in it. And in order to call add, I need to execute two statements. So another thing you can do is, so in this strategy is to just take that statement, put it here, and get rid of the procedure entirely. It's called inline. So the compiler also might do that. Now whether it does that or not is going to depend upon the size of add. So if add is just, two statements, two instructions, then it's certainly going to inline. But if it was 50 instructions, then, in terms of code size, putting 50 instructions for every call will make the code bigger. And in terms of the savings you get, here I'm saving 1, 2, 3 instructions, right? 4 instruction goes to 1. So that's a big savings. But if this was 50 instructions, then it'd be 54 versus 51. Not a big savings. You see the trade-off. The compiler will choose to put things, arguments in registers if the callee is small. If the callee is really big, it's going to need all the registers. So it's going to have to go to memory anyway. And also if they're in the same file, so it can change its calling strategy. And it will not save the return address if the callee is small and the leave procedure. It doesn't call anything else. Okay, so those are optimizations you might see. Any questions? All right. That just summarizes what we talked about. So, as bad as the midterm was, the final will be worse. And this is why. So, what does this code do? How long would you like to answer this question? We have 40 minutes left in class, there's 35. If I gave you 35 minutes, could you answer this question?
Yes.
Oh, excellent. How would you do it?
Start with high-level comments.
Start with high-level comments. And then what? Have 10 shots of espresso. Then what? Arrows and boxes, exactly. Find the structure. So if you just stared at the screen, 35 minutes would not be enough. 3 days would not be enough. Okay. But if I ask you what this does, what does it do? Raise your hand when you know. I'm timing. Then I'm recording it. Great. Yeah, that's why I'm recording it, Gregor. It is recursion. Yes.
Is it like?
No, don't tell me the answer. Just raise your hand when you think you know the answer. Okay, so yes, now you can tell me. What does it do?
It's the exclamation point, thing where you go 5 plus 4 plus 3 plus 2 plus 1. Factorial, yeah.
Yeah, except it's factorial with addition, not factorial multiplication. It just sums an array recursively. Right? Each step is adding the end of the array to the rest of the array. So that took you maybe 30 seconds. Let's see. It's the same program. That's what that does. Why is it so much easier to read this? Well, because we designed it that way. But like if I were to bring in a bunch of English majors, nothing wrong with English majors. No computer science, and I asked them, what does that do? Would they be able to answer it? No. The reason that this is easy to read, I'm going to tell you, it's 2 things. One is that it's small, and 2 is there's a whole lot of embedded knowledge here. You know when you see if, you know what that means, right? So you didn't have to figure that out. Now, there's an if over here. That's what it means, right? But you know that. This if, you have a different model of what if is. Not like how it works, like the mechanism, what actually happens when if executes. You have a higher, more abstract idea. If is an abstraction of that. Same thing with procedure calls. What really makes this hard is procedure. So this has inside of it a procedure call, which you can find. You can find the procedure call. It's not hard, right? Find it right now on the left-hand side. Right, it's just a jump, and then well, there's a GPC above it, And then maybe you have some arguments, you go up, actually you keep going up until you see it stopped messing around to R5. And that's probably all the arguments. Okay. But on the right hand side we see the procedure call, but in addition to that, you are familiar with recursion. Because a recursive procedure call is not necessarily easy to understand, so again, there's all this embedded knowledge you have. With this abstraction, it's a small thing, where on the left-hand side, it has all that stuff there, but there's no structure, and it's big. So, I'm just going to go through an exercise. The point of this is to illustrate how this structure benefits us in understanding. What I'm going to do is I'm going to remove one little bit of structure at a time. So the left-hand side will be the previous version, the right-hand side is a new version. So in the very first step, what I'm doing is removing types and variable names. Because that's something that is part of this embedded knowledge. The int star, you know now, that's probably an array of ints. Variable whose name is n is probably the size. Maybe it'll even say size and array. But when you look at this code now, there are no types. And also the names are meaningless because, with register names are meaningless. But you can still do that though, right? It's slightly harder because you won't know what these two arguments are until what? Until you get right here. But as soon as you see that, now you know that A0 is an array, and it's used as an array. And you'll know that A1 has something to do with the index. Okay. So this is not so much harder. The next step, I'm removing the structured if, and replacing it with a go-to if. Okay, still totally valid C, but harder to understand. Oops. Elder hazards. Okay, so here we can very easily see that here's the code that executes in the then path. Here's the code in the else path. I mean, the point of the structured if is to make those two things very clear. But over here, it's not so clear, right? Because here's this thing, then you go to here, and then here you go to there. So you actually have to find those go-tos to see where this is. Still, like, if this was like 95% beautiful, what is this? Whoa, 70 really? Maybe like 85 or something. The next step, I'm going to change the way the values are returned by putting them in global variable names, R0. So over here, I'm returning 0. Here, I just set R0 to be equal to 0. And here I have, I'm using the value that the procedure returns. Here, I call the procedure, and then just use R0. Perfectly valid C, it would work, but definitely harder to read because the connection between the procedure call on the line above where the pointer is and this value is now less clear. Now you can remember, oh, it's R0. Now, maybe this R0 wasn't produced by the procedure, but if you look at the procedure and you see, oh, it's changing R0. So when you call the procedure, probably I can use R0. Also, because this is a recursive call, it's kind of confusing because there's the two R0s. There's the R0 from the procedure that's running and the procedure that you call. Right? That's just recursion. I don't know what are we at now. 70% maybe? Oops. Okay. So what I've done now is remove the procedure call and remove the arrays. Still, this is actually perfectly valid C. I'm using an array called mem to represent the stack. So I do these things I need to do at the beginning. subtract, so this is the pointer to an int, so I'm really subtracting 4 by subtracting 1. I save the return address. Then I read the arguments from the stack. Right? That's what this means, right? We know that A0 and A1 are on the stack somewhere. And if I want to use them here, they have to be read from the stack, so I'm just doing that. And now I have the if statement. I'm just going to go to the next step where I'm just taking this and expanded it out so you can see the correspondence between the code on the right-hand side and the left-hand side, and the code that was added on the right-hand side. So that's the same. Now here's the procedure call. I have to make room for the 2 arguments and save them. Set the return address into R6. Jump to the procedure, right? Instead of the procedure call. There's no procedure call anymore. And at the end, I have to undo what I did here. And then this step right here is reading the array. Right? That's the base address, that's the index. That's this part. And then go to L1, same. That's the same. And then at the end here, I'm undoing what happened here. Significantly harder. We're down to like 0.3 or something like that, right? Because of the procedure call. So it's definitely when you get to procedure calls. So here I'm just swapping a few things around, changing all of the variable accesses now to use register names. They're just basically the same. What's on the left is C, what's on the right is SM213 assembly. Both completely incomprehensible. Right? So this problem that you thought you had with this class, which is you thought it was assembly language, it's not. It has actually nothing to do with assembly language. It has to do with the taking mechanisms that are in a high-level language, abstractions, removing the abstraction and having to deal with the implementation all at once. And the only way to do that is to be able to spot the abstraction and recreate it. And that's how you'll understand this code, which is what everybody said. So there's the assembly. First we comment it all, then we draw the lines and boxes. And having done that, now I'm not going to go through this in detail. You can look at it, over the weekend, whatever you want to do. But you'll see that I've identified the big green box is the procedure call. I have the body of the procedure. I've got this if statement here, the then and the else, and I've got the procedures epilogue and prologue. And each of those boxes is a relatively small number of things. So here, in fact, this box can be separated into, further into 3 boxes, which it is, but you may not see it. Saving the arguments, making the call, the epilogue, the call. And so when you do that, each of those sub-boxes has fewer than 7 lines in it. So the box itself is fairly easy to read. Plus it follows a pattern, which you know about. Questions? Okay. So it's not assembly language that's the problem, no matter what people tell you. Okay. So now we're going to move on to looking at, there's 2 things that we've learned, that you've learned, that combine together to explain how viruses, one common way that viruses attack programs. Yeah, so the first thing is, wait, you said C is dumb. Or is it C or C programmers that are dumb? I don't know. So the first thing is that C does not do array bounds checking. And the second thing has to do with the stack. So this is a program that is representative of a lot of programs. Virtually all C programs that are interesting have a bug like this in them. Virtually all programs that are internet-facing, that are part of the internet implementation, or the operating systems of nodes on the internet, are written in C. Virtually everything. All the routers written in C. All the operating systems in the routers are written in C. All the operating systems are written in C. And web servers and all that stuff is written in C, mostly. Even though you might write JavaScript for your individual web application, the server itself is probably like Node.js. I don't actually know, maybe it's not. Anyway, it doesn't matter. Lots and lots of programs have this bug, and this bug is exposed to the internet in lots of places. The bug is here. It's just simply the string copy bug that we looked at earlier. So that's where the bug is. That loop is the same as this loop. You can take a look at this loop instead of that loop. It's easier to read. So here I have a procedure that has a local variable that's a statically sized array. So it has an array of 10 things. And it has a pointer to it that it's using to access the array. It goes through a loop until it sees a particular character in the array. So it is copying a prefix of the array up into the first dot into this local variable so that it can do something with it. And this would be, for example, and I'll show you in a few minutes, that this bug showed it was in a very famous case in a web server. So maybe this is code that is parsing the URL. Get everything up to the first dot, then we'll do something with that. And the size here was set based upon an assumption about how far you would go into the string before you got to the first dot. Which, if the string is properly formed, if the input's properly formed, perhaps it'll always be in the first 10 characters. Okay? But it doesn't check to see if it is, and so if the string is malformed and the first dot is beyond 10, then it's going to overflow that array. This makes sense? And it's going to overflow it with the contents of this variable string. So string is an array. It's the input that the print buffer. And in this program, that value is input from the command line. So now look at the rest of this program. So what this program does, it has another buffer. It prints that it's starting, and then it calls get input that does an f read from standard in. So that's the command line. To read whatever you type here, returns that value, and then that is stored in input, and actually copies it into input, and then that becomes the parameter to print prefix. So print prefix is getting a string that comes from me typing something on the command line. And so if I type something that's bigger than 10, something bad will happen. So what do you think will happen? Yeah, but I mean, when I run it, what do you think? What symptom do you think I might see? So that's the correct behavior. Everybody see that? Let me switch this over. And that's the incorrect behavior. What did it just do? I don't know. It didn't print done. It's in some kind of infinite loop. I was hoping to get a difference in this. I guess I can. The problem with this bug is it is non-deterministic what's going to happen. Well, that's what's going to happen. It might have segmentation fault, but it didn't. It went into infinite loop. And the question is why? So what happened? Let's look at why. So we know that it is overflowing this array buff. But the array buff happens to be on the stack. And And so what it's also overflowing the current activation frame. So here's a picture of the activation frame. It has, so buff is an array of characters. So I'm showing each of those characters is a single line in the activation frame. Right, so that's buff 0 to buff 9 is the first 10 bytes. The next thing is a pointer. That'll be 8 bytes long. And there'll be 2 bytes of filler there, actually, to get that line. Well, actually, there'll be 6 bytes of filler because it's 8 bytes. And then BP and RA and STR, which is also, STR is the argument. They're all 8 bytes long. So, this is like not to scale, but that's what's in the activation frame. That make sense? And so, as this loop goes, it will write something. The first thing I type goes into buff 0. The 9th thing I type goes into buff 1. The 10th thing I type goes into buff 9. The 11th and 12th and 13th start to go over top of these things. And at some point, I get to the return address. And I write over top the return address. Now, why is that a problem?
Because then it won't be able to continue control flow because it'll be jumping to the wrong address.
Right, so at the end of print prefix, there's going to be a load from a certain location of the stack. I don't know what that is. I mean, we can calculate it. It's going to be, what did I say? It's 16 bytes to get to BP, another 8, so it'll be 24. So maybe it's offset 24 from the stack pointer. And that's 8 bytes, this is 4 bytes, so maybe, I don't know, it's just a number anyway. So someplace we have that. And some other things, changing the stack pointer, R5, adding something to it, and then there's this. So whatever value is stored in memory at that location on the stack becomes an address that the program jumps to. So it didn't return to, so the thing that calls print prefix is main. So it didn't return to main, so it didn't print none. Because the only way to return to main is to have the correct value in there. So this is called a stack smash. What I've done is I smashed the return address with something in the string. Now it was just gibberish, right? So I was hoping, and I'm not exactly sure why, it didn't just give me a segmentation fault. They jumped to some weird address. But in any case, something happened. We have to diagnose it further, but it didn't jump to the place I want. So how does this get?
Before you wrote into the return address, wouldn't you have written into BP?
Yep, I have. Yep.
Which would be pointing to some random place in memory. So, what's the chances of the return address actually being affected?
So what you're observing is that in order to get to the return address, to smash that, I've got to smash everything on the stack above it.
Yeah.
And it's possible that by doing that, I'd cause some other error in the program, and it would stop before it copied to our over the return address, and that's possible. In this case, what happens is the code is the code on the left that's using BP, but since that's a very small set of code, the compilers generate code to keep BP in a register. So I've smashed BP in memory, but it never reads from it. If it did read from it, this attack wouldn't work. Yeah, it's a very good observation. That's what's happening. So how does this create a vector for infection? Well, that string is coming from outside the program. So the person who has control over the content of that string now gets to decide to what address the program will jump to. Now, in this case, the attacker's goal is what's called remote execution. So I want to get the attack program, I control the string. I want to get the attack program to execute code that it didn't intend to execute, that I control. And in fact, what I'm going to do is I'm going to give it the code to execute. So I'm going to create a string that inside the string has a program. And I'm going to get it to execute that program. And now you think about, well, if that program's on the internet, and that string is coming in from the internet, now anybody who has access to the internet, or your program through the internet, now to present a string like this and get that program to execute the string. In the lab next week, we'll show you a little bit different version of this on Monday to help you with the lab. You're going to do this, and we're going to set up a server, and you're going to infect the server with the virus and get it to run a shell. So you can do anything you want with the server. Okay, so, but for today, just the basic ideas of how this works is that here are the key things I need. I need a buffer overflow somewhere in the program on the stack. Yeah, question?
Just like historically, like, why did like the C language and C come from It seems like something we would catch.
Can we say that question just for a minute? So I need, this was the stupid C. Trust me that you're no smarter than people were in their 60s and 70s. You just have knowledge of things. So, so I need this array overflow. It has to overflow something on the stack, and then the string that is overflowing, or the input that causes the overflow, has to be controlled from outside the program. And programs are filled with these things. And if I'm an attacker, I will have access to the program I'm going to infect. I can run it on my machine. Because I'm attacking, you know, Mac OS, or I'm attacking the Apache web server, or I'm attacking something in an internet switch. You know, either public domain code that I can get the source code for, or proprietary code that I can buy the binary. So I'm running the code on my machine, trying to find these bugs. And one way to find the bugs is to read assembly. So this is, there's a lot of, if you're using this to make money, there's a lot of money in reading assembly code. You can do this. And I find the bug, and then I have to do a couple of other things that I'll explain in a second, so that I can create a string that will activate that bug in the way you looked at here. Well, I get to smash over the return address and then write the virus code onto the stack and change the return address so that it points to the code. So that this value here, which goes into R6, so here's the stack, and here is the return address, points somewhere else on the stack below it, and then there's the virus. Now, you know that programs are just numbers, so this virus is just being encoded as numbers in a string. Now, there's many things hard about this, and in fact, this particular attack done this way, there's a number of preventive measures that wouldn't allow this attack to work. So don't worry that I'm giving you, too much information for you to handle, and you'd be tempted. Although there probably are programs that would work, and old operating systems. But one thing that's hard is that I have to guess. I have to know what address this is at. Right, so the stack is going to be some address. This is going to be some address. Right, so stack's here. It's going to be somewhere, and I have to know what it is because I have to change when I smash the return address, I have to smash it with an address that's here. To make this easier, I can include it before the virus something called a no-op sled. So no-op is an instruction that does nothing. So if I have a whole bunch of no-ops, as I've shown you here, and then I jump into them somewhere, it's either the first no-op, the middle no-op, the last no-op, it doesn't matter. I just slide through all the no-ops doing nothing, and eventually, if what's after all the no-ops is the virus, I execute the virus. So now I just have to approximate, I can have like a megabyte of no-op, so I approximately get the stack address, but I still have to be pretty close. Okay. Here's my virus. So this is IA 32-64 assembly code. It's just different assembly code. This is my attack string. So the 2020, those are spaces. This is printed out in text. This is a file. What you see next is the return address that I'm going to smash over. I just write it over and over and over again. I don't have to know exactly where the return address is. I'm just writing this number a bunch of times so that one of them is going to go over top of the return address. Next, the green stuff is the no-op sled. So that address has got to point somewhere into the no-op. And then the red stuff is in hex. It's that code. That's the virus.